You to settle in, please. Yeah, so this is the final talk of the conference. It's my honor to welcome Professor David Vogan of MIT, who will speak on generalizing endoscopic transfer. Professor Vogan.
Is the volume okay? I know some of you would prefer if there was no volume at all, but so Dragan dealt with this duty at the drinks last night, but now that we're all sober, I think it would still be a good idea to thank again Dipendra and Aprameo and all of the hosts here, everyone who has taken the foreigners and the incompetent and made them feel welcome and at home. I'm very, very grateful. Okay, so I expect you're all tired, so I will try not to exceed my allotted time. So this is what I want to talk about. I want to tell you a little bit about what I understand of endoscopic transfer and how, I didn't, let's see, did the previous slide, oh shoot. I didn't write on this slide that my collaborators on this work are Jeff Adams and Steve Miller. That's a serious error. So I want to talk a little bit about the Langlands and Shellstad idea of endoscopic transfer and how and why we want to extend it a bit. So, okay, so somewhere I wrote their names. That's absolutely right. I misread. So I talk every week with Jeff and Lucas and Steve Miller and Mark van Leuven, and every thought that I have is joint with some combination of them, or more often stolen from some combination of them. And so I apologize to Steve Miller and to Lucas, what's his name, but these people are just, they're part of how I think now. So the actual theorems that we have, it is the last talk. I'm not going to inflict theorems on you. The theorems concern only real reductive groups. But real reductive groups are technically awful. I remember writing a letter to Paul Sally once, addressing it to the Department of P-adic Analysis with the slogan, if you can add, you can integrate. And so R is worse, and so in this talk I'm going to concentrate on p-adic fields, even though the theorems are about the real field. Okay, so non-Archimedean local field K and a connected reductive algebraic group over K. And there are still more difficulties, but I'm happy to ignore difficulties. So, of course, what we want to do is understand the representations of a reductive algebraic group over a local field. I'll be slightly more precise, but an endoscopic group is a smaller reductive group, perhaps not even contained in G, but smaller. And, well, here are some examples. I learned from Roger Howe that the best reductive group in the world is the symplectic group. And if you have a symplectic group of size, well, rank P plus Q, then there's an endoscopic group, SOPP cross SP2Q, which is not a subgroup. Another endoscopic group which is a subgroup is this one, this one here. Endoscopic transfer carries virtual representations of this smaller group to virtual representations of G. So what Lucas and Jeff and I have done is enlarge the Langlands-Shellstadt definition of endoscopic group. We have a larger class of these groups H, and still have a notion of endoscopic transfer. So here are two examples of groups that are endoscopic and are, well, generalized endoscopic groups. There they are. In this big symplectic group of dimension of rank P plus Q plus R, you can have an endoscopic group which is UPQ cross the symplectic group of rank R. Excuse me. In GL2P plus Q, this is a nod to my old friend Birgit, you can have one of these generalized groups which looks like GLPC cross GLQR. Actually, both of these are subgroups of G. Excuse me. Okay, so what's the connection with Harishchandra? So Harishandra's work that we've heard about again and again, one of the most magnificent accomplishments that he made was the description of discrete series representations. Excuse me, I may have a cough drop in my pocket, and that would be good. Oh, thank you. Thank you. So, what Hermann Weyl did to describe, to calculate character formulas for compact groups was he found a formula for integration in compact groups, the Weyl integral formula, and the Schur orthogonality relations for characters, and these two things, almost from nothing else, handed him the Weyl character formula. So Harishandra's work was exactly the same thing, except that every step was incredibly harder and required enormously deep new ideas. So one of the ideas, which I'm not sure has been discussed a lot this week, was Harishandra's method of descent. So Harishandra said that if, well known that if you have a semi-simple element of a reductive group, then the centralizer of that semi-simple element is again a reductive group. What Harishandra descent does says that if you have this a character on G near the element S, that can be described completely in terms of some new character, theta H, on this smaller group H, the centralizer of S. So formally, Harishandra was not a fan of formal, but I'll do this. If you write K of G for the lattice of virtual representations of G, then Harishandra was defining a map from virtual representations of G to virtual representations of H. So what I'm The point of view that I want to talk about today is that endoscopic transfer is Harishchandra descent on the side of the L group. This statement is precisely true in the Archimedean fields. For non-Archimedean fields, it isn't exactly Harishchandra descent which is in question, but it's a very similar kind of mathematics, similar technical tools. So that's what this has to do with Harishchandra. So in order to talk about this, well, to talk about a group, you need to give it a name. It's something to put in the abstract of your paper, is the name of your group. So how do you give a group a name? So Lee and Chevrolet and Grothendieck explained how to do this, that if you have an algebraically closed field, they showed that you could attach to your reductive group a based root datum. I'm not going to go through the whole definition of a based root datum, but did I write anything else? Yeah, you pick a maximal torus in G, and then X upper star is the lattice of characters of that maximal torus. X lower star is the lattice of co-characters. Inside the character lattice, X upper star, is this finite set pi, which is the set of simple roots of G, and inside the co-character lattice is this finite set pi check of simple co-roots. And, well, a lattice is isomorphic to n tuples of integers for some n. So to write down this name of G, well, you just have to say, okay, I'm going to let my lattices be Zn, and I'm going to tell you these finite sets. These are n tuples of integers. Finite sets of n tuples of integers. I'm sorry, I am going to, since my pocket failed me, I will, where did, oh, I left it up there. Thank you. My wife would say that this cough drop had expired 6 months ago, but that's, she doesn't have a conservative attitude. It's perfectly good. Paper is good for you.
You know you're being recorded, right?
Oh, shit. Okay. So, here's, well, you need to know, of course, when two of these names define the same group, and the answer is that if there's an invertible n by n integer matrix M that carries, well, the set pi to the other set pi, and the inverse transpose of M carries pi check to pi check. So here's an example. The name of G2 is given by these two singleton sets of two tuples of integers, the integer 1 minus 1, and the other one is also the integers 1 and minus 1. So great. The exceptional group of type G2, you can write its name like this. So actually, another thing which is wonderful about this naming convention is that computers can understand it. You don't need to know a great deal about computer programming to be able to input n tuples of integers. So that's good. So, well, what I said on the last slide is that to name a reductive group over an algebraically closed field, basically you have to write down two finite sets of n tuples of integers. If the group is actually to be defined over a field little k that's not algebraically closed, then you get an action of the Galois group on this based root datum. So that means that you have a representation of the Galois group by n integer matrices with these two properties that each operator in the Galois representation permutes the simple roots and permutes the simple co-roots. And I haven't written down the axioms for a based root datum, but of course this Galois action has to respect those axioms. So to a first approximation, this means you have an action of the Galois group on the Dynkin diagram of G. So two rational forms of G are called inner if they correspond to the same action of the Galois group on the based root datum. So now we've got this really concrete way of partially describing a group over any field. We've got this based root datum and this action of the Galois group on the based root datum. So, for example, a rank 2 unitary group over a field begins with a, say, separable quadratic extension of K, which is to say a subgroup of the Galois group of index 2. And this is an inner form of GL2. I wrote the root datum for GL2 on a previous slide, and the Galois representation on Z2 sends any element of this big subgroup, gamma naught, goes to the identity, and any element not in the big subgroup goes to this matrix of order 2. And the nice thing about this matrix of order 2 is that it fixes the simple root, the 1 minus 1. Right? This is a good linear algebra exercise. Apply this matrix to the vector 1 minus 1. What do you get? It's easy to grade. Anyway, so all the unitary groups with a fixed quadratic extension field, they make a single inner class of rational forms. Okay. So Langlands in the 1960s, Langlands was a very concrete, analytic, mathematician. He was working very hard with Eisenstein series and Paul's Eisenstein series, and he had really difficult calculations with roots and weights to do. And he tried to understand how to express these roots and weights calculations in a more natural way. And what he understood was that the calculations he was doing were better thought of not in the group G that he was interested in, but in the Langlands dual group. So here's the story. I said you've got an action of the Galois group on this based root datum. The axioms for based root data are unchanged if you interchange the two lattices and these two finite sets. So you have a dual based root datum where you've replaced this character lattice by the co-character lattice and vice versa. And the Galois action just comes along for the ride. So you get an algebraic dual group, check G, and an action of the Galois group on check G. This Galois action here is not the kind of Galois action that comes up for rational forms. This is gamma acting on check G in a purely algebraic way. There's no complex conjugates or anything in it. So this L group is more or less defined over Z. So Langland's insight was that the representation theory over a field K of this rational group G of K was related to algebraic geometry on this L group if you took the capital K points. So, for example, we're very often interested in complex representations. K is a local field, so the statement is that complex representations excuse me, of this group over a local field are related to complex algebraic geometry of this complex L group. So I'm not telling you anything new here. Endoscopic and generalized endoscopic groups both correspond to certain subgroups of the L group. So this local Langland's conjecture says that if you want to relate representations of this little group H to this big group G, that means you have to relate the algebraic geometry of this big L group to the algebraic geometry of this complex subgroup. Nothing to it. The question is, what is this little squiggly arrow? This is left-right squig arrow. I love this symbol. How is it that the representation theory on G is connected to algebraic geometry? Okay, well, answer has to do with the Wedelin group. So if K is a p-adic field, it has a Galois group. And I talked about this complex L group. And I said that local Langlands should tell you how to understand representations of G of K using this L group. So this p-adic field K has a finite residue field FQ. The Galois group of FQ is naturally Z hat, and so that gives you a natural short exact sequence from the Galois group onto Z hat with kernel, this is called the inertia subgroup. The Galois theory for the finite field is really simple. This Z hat comes with a preferred generator, Frobenius. The inertia subgroup is, of course, a profinite compact group. So the Weil group you get as the preimage of, you take the copy of Z generated by the Frobenius element inside Z hat, and you look at the preimage. So the Weil group ends up with a short exact sequence. You have this compact profinite inertia group. Here's the Weil group, and the quotient is Z. The Wedelin group, everybody gets this wrong. Everybody wants to write the Weil group across the SL2C, that's wrong. Deligne defined the Weil-Deligne group to be the semi-direct product of the Weil group with C. And the semi-direct product, well, you have to give an action of the Weil group on C to define this semi-direct product. And the action is that the inertia group acts trivially, and the Frobenius element acts by multiplication by Q. Okay. By the way, you should feel free to stop me at any point. If you have an interesting question, I'll sit in the corner and cough and rummage through my bag while you say your interesting question, and then I'll say, I'm not sure. But so I'm happy to do that at any point. So, what's a Langlands parameter? We've got these two short exact sequences. The L group has this complex dual group sitting inside the L group, and it's actually a semi-direct product, quotient gamma. The Weil-Deligne group has a normal subgroup C, and the quotient is the Weil group. A Langlands parameter is a group homomorphism from the Weil-Deligne group to the L group that's compatible with these exact sequences. So you have a map from this nilpotent algebraic group C into the dual group, and well, that's the picture. That's what a Deligne-Langlands parameter is. The local Langlands conjecture says that to every such phi prime, you can make a finite L packet of irreducible representations of your rational group. So, a stronger state, well, what's more, these L packets partition the representations of G of K. Any representation of G of K appears in exactly one L packet. Well, I should have said that this packet depends only on the check G conjugacy class of this parameter. And if the rational group is quasi-split, then this L packet is not empty. Okay. So this is early 1970s mathematics. So what I want to do is make more precise statements about how the representations of G of K are related to algebraic geometry problems about parameters in the L group. So I want to define, remember that phi prime is a homomorphism from the Weil-Deligne group to the L group. I want to define the infinitesimal character of phi to be its restriction to the Weil group. So if you have an infinitesimal character, there are, up to conjugation, finitely many ways to extend it to a Weil-Deligne parameter. And so those are the parameters of infinitesimal character phi. So am I going to say something about this? Well, I said something about this, but I think I don't want to. I don't want to dwell on this. Somehow, out of this phi, you get a reductive algebraic group, check G phi, and you get a nilpotent subalgebra of the Lie algebra. And this reductive algebraic group, check G phi, on this nilpotent Lie algebra, and it acts with a finite number of orbits. And these orbits of check G phi on this nilpotent Lie algebra, those are the Langlands parameters. So it's a finite number of orbits, and the algebraic geometry we want to study is the geometry of those orbits. So what happens is you may not know if you haven't studied algebraic geometry, but a vector space is a smooth algebraic variety, but the closures of these check G phi orbits do not have to be smooth. And so what we want to do is understand perverse sheaves on those orbit closures in the vector space. Yes?
What do you mean by the infinitesimal character of the parameter in the
This is what I mean. I define it to be the restriction to the V group. It's just an analogy kind of thing. In the real case, the corresponding statement is that the infinitesimal the V group in the real case has a subgroup C. Now I've been blanking out. C cross, and if you restrict the real Langlands parameter to that C cross, that's telling you exactly the infinitesimal character of the real group representation. So this is my, I don't know anything but real groups laziness, so I'll just call this the same. Yes?
In the real case, there is no information that the
No, I don't believe, sorry. I said at the beginning that one of the reasons I didn't want to talk about the real case was that the usual definition of Langlands parameters in the real case is wrong. It's the actual infinitesimal, so you have to do this corrected version of Langlands parameters in the real case, and then there's an actual element of a semi-simple element in the dual in the Lie algebra of check G. That semi-simple element is the infinitesimal character. So you're right. It isn't exactly the C cross. It's not exactly the restriction to C cross.
So we should take this just the holomorphic to understand what this is?
I'm sorry?
To understand or to translate what you're saying next in the real case, should we take just the holomorphic part, or?
I think that's probably right. I mean, you should use the correct Langlands parameters from the ABV book, and then the infinitesimal character is handed to you. Sorry. Okay, so, well, as I said, this vector space is pre-homogeneous, and so the question of the singularities of orbits and the nature of orbits, this has been studied for decades. Okay, so I think I'm probably not gonna repeat this, but, well, I do have, the conclusion is that there's this reductive subgroup which is acting on a nilpotent Lie algebra with a finite number of orbits, and the extensions of this infinitesimal character to a full Langlands parameter are given by orbits. The local Langlands conjecture says that irreducible representations of this infinitesimal character should be in one-to-one correspondence with check G phi equivariant perverse sheaves on this nilpotent Lie algebra. and this is one of the places where I'm sweeping some things under the rug related to pure versus not pure inner forms and so on, but more or less this is a reasonable thing to think. Okay, and a Langland's L packet corresponds to all of the sheaves, well, all of the constructible sheaves with support on this orbit. I haven't said that properly. The Langland's L packet corresponds to the irreducible perverse sheaves whose support is the closure of this orbit. Okay. So I said that an L group had this short exact sequence. An L subgroup means that you have a smaller reductive group, check H, sitting inside check G, and that's sitting inside, well, some subgroup of the L group, and so what you want is that it maps onto, oh shoot, it maps onto the Galois group.
Does reductive still be connected?
No. I mean, at this level, I'm being a little vague. For the endoscopic things, I'm going to make them connected. So when you have an extended, well, an L subgroup like this, and you have a parameter for this EH, so that's a map from the Wedelin group into this EH, then it trivially just use this inclusion of EH into LG, you get a Langland's parameter, a Deligne-Langland's parameter, which I should have called phi prime, sorry, for G. And these nilpotent Lie algebras, well, there's a containment like that. And the reductive group that's acting on these nilpotent Lie algebras, there's a containment. So this is the geometry that underlies Langland's functoriality. Langland says that when you've got an L subgroup like this, then there should be some relationship between representations, automorphic, well, local representations related to this H and local representations for G. Well, so there's the statement. If you want to relate representations of G to representations of H, what you have to do is relate perverse sheaves on this big space here to perverse sheaves on this small space. That's kind of easy. I mean, there are easy functors that go from, for example, a perverse sheaf on this big space to in some derived category of perverse sheaves on this subspace. But in order to say something about that, you need, this shouldn't be a sort of random L subgroup. You need more information in order to get a nice relationship between these things, a relationship you can say something about. So the kind of strong hypotheses that I want, and I want to use this Goreski-McPherson-Lefschetz formula, and I don't think I wrote any words about it, but what Goreski and McPherson did, they said if you have some nice variety, then you want to look at perverse sheaves on that big variety. if you have a nice automorphism of the big variety, then you can look at the fixed point set of the automorphism, and Goreski and McPherson tell you strong relations between the perverse sheaves on the big space and the perverse sheaves along the fixed points. That's this Lefschetz formula. And as I say, what it depends on is that the subvariety should be the fixed points of an automorphism. So how do you do this? Well, the story is I've got Langland's parameters, which are some kind of check G orbits on an algebraic variety. An element of the dual group therefore gives you an automorphism of this space of Langland's parameters. I mean, it's a space with a check G action, so if you have an element of check G, that's an automorphism. A Langland-Shellstad endoscopic datum is a semi-simple element of check G together with an L subgroup of which sits inside the fixed points of S on the L group. So S acts on the whole L group, and you can look at the fixed point group, and the Langland-Shellstad requirement is that you should be sitting inside the fixed points on that big space, and what you want is that this identity component of your L subgroup, well, should be the identity component of the central of the fixed points of S. So Janos was asking, do I want this centralizer of S to be connected, or, well, the centralizer of S is allowed to be disconnected, but then I want to use the identity component of the centralizer of S. So in this setting, this check H is a reductive group, so it has a root datum, and that has a dual root datum, and there's a Galois action, and so you get an inner class of rational forms of H. Well, yeah, that's what's written here. And so the definition of an endoscopic group for G is that it's any one of these forms in the inner class defined this way. Once you have this stuff on the dual group, that gives you an inner class of forms of H, and any one of those inner forms you call an endoscopic group for G. Well, now I'm slipping away from my blind allegiance to Langlands and Shellstad. Langlands and Shellstad, I think, would always want this H to be the quasi-split form, but I don't want that. Okay. So where's the fixed point formula? Well, I'm not going to say too much. The Goreski-McPherson formula basically tells you that if you look at in this setting that you've got some perverse cohomology up on G, and this S is giving you an action on it, then the trace of that action can be computed on the level of the fixed points. That's what a Lefschetz formula does. It says that some computation in cohomology can be done along the fixed points. Yes?
Before you defined, I think, parameters as G-check orbits.
Yes.
But here you mean actual parameters, right?
Yes. Well, so, yeah, I should have, I didn't make this terminology very clear. I think I should make a parameter an actual homomorphism, but equivalence classes of parameters are G-check orbits. Okay. And well, in order to do this, it seems that you have to have S central in this extended group. So what's written here is a way of thinking about the Langlands-Shellstad theory, and it doesn't seem possible to extend it. So here's what we did. We said that a generalized endoscopic datum is just like Langlands and Shellstad. We start with some S, and then we want an L subgroup of LG, but instead of asking it to be centralized by S, we only want that it's normalized by S. And we want this identity component of the L subgroup to be the identity component of the centralizer of S, just as in the Langlands-Shellstad theory. And well, in the real case, this issue doesn't arise. I think maybe I want this setting gives you an action of S on the Galois group, and maybe I want that action to be trivial. I wrote these slides a long time ago, and I have no idea why I put that. There was probably a good reason. So, just as for Langlands and Shellstad endoscopic groups, you do get a Galois action on the root datum, and therefore an inner class of K-forms, and these K-forms are what we call generalized endoscopic groups. So, well, there's some nastiness here. I want to define a map from this extended group for H to check H by, I conjugate by S, well, it's the commutator of the element of EH and S. And another way to, well, this function C is telling you how much S fails to commute. You know, I assume that S commuted with check H, but when M is outside of check H, this commutator can be non-trivial, and so this function C is measuring the failure of this extended group to be a Langlands and Shellstad endoscopic group. Okay, so well, as I said, the S does commute with check H, so you end up with a map from gamma to the center of check H, and it's a one cocycle of gamma with values in the center. So what I need to get endoscopic transfer is a map from sheaves on LG parameters to sheaves on these extended group parameters. And in classical endoscopy, you have this conjugation action on LG parameters, and the fixed points are the parameters for H. And what do I want to say? In the generalization, S still acts on the parameters for G, but it does not fix the parameters with values in H. When you conjugate by S some parameter taking values in this EH, you get this twist by this cocycle C of gamma. So anyway, well, I don't want to mess with this. The bottom line is that to make an action of S, well, to get an action of S which has fixed points, parameters for H, you need to compose the adjoint action of S with multiplication by this one cocycle. So I don't want to get into this. The point is that in the original Langlands classification, one of the desiderata that Langlands wrote down was, suppose you have a one cocycle of the vague group with values in the center of the dual group, and you use it to twist your Langlands parameter, then you get a new Langlands parameter, and what happens is this one cocycle, by class field theory kinds of stuff, gives you a one-dimensional representation of the rational group G of K. And this desideratum for the Langlands classification was that multiplication by this cocycle corresponds to tensoring representations of G of K with this one-dimensional. So anyway, I'm not gonna talk about this. I'll just say, if you have any rational Levy subgroup of G, then you get a Galois action on the root datum of L, and well, more or less you can get an extended group inside the L group. But this extended group is usually not an endoscopic group in the sense of Langlands and Shellstad, but it is a generalized endoscopic group. So the point I want to make is that this endoscopic transfer from a general rational Levy like this is an important generalization of parabolic induction. So over the reals, this is done by Greg Zuckerman. It's cohomological induction. Over p-adic fields, it's mostly completely mysterious. Harishandra would tell us to get to work. I will stop there and say again thank you very much for a completely exhausting but completely delightful week. Yes.
Well, finite field is the limit theory that looks a lot like starting from torus.
Yep.
Is that?
Oh, of course, absolutely. I mean, in the p-adic case, if you start with an elliptic torus, then you should be able to construct from a character of an elliptic torus some sort of character on G, and this is really hard work, but this is what many people have done. There's a lot of progress, and it is extending the Deligne-Lustig finite field thing, which corresponds to depth zero representations.
Your definition of endoscopic groups, you didn't mention the problem which occurs naturally in with Shellstad and for good cause, which is that when you define the L group, you need an action of Galois, and for the L group to give you the right parameterization for Langlands, for the Langlands correspondence, you need that condition that it fixes a Borel and an épinglage.
Sure.
And so, of course, you impose that on G, but then you have a problem.
Of course, and what Adam Tamsin Barbash and I did in our book in 1992 was we said, if you drop this semi-direct product condition on the L group, then the Langlands parameters into that wrong thing parameterize representations of a certain linear covering group of your original group, and so it's fine. So this is one of many things that I swept under the rug here, but so the endoscopic transfer will, if this EL is not actually an L group, then you'll have transfer involving not exactly representations of L, but some cover of L. For example, there's some half sum of positive roots in a nil radical, which defines a square root of a character of L, so you get a double cover of L, and really you're lifting from that double cover.
It's an algebraic problem.
Yeah.
And of course, the same things comes with the Langlands for your ELs.
Mm-hmm.
Even more complicated. Yes?
Yes. Yes.
Could you briefly state the theorem over R?
The theorem that we were interested, I suppose the main theorem we wanted over R was that any Arthur packet was obtained by cohomological induction from a unipotent Arthur packet. And furthermore, for a unipotent Arthur packet, if the SL2 part, the nilpotent part, is not distinguished, then that unipotent Arthur packet is also obtained by real or cohomological induction from some levy. A nilpotent is called distinguished if its centralizer does not contain a torus. So in E8 there are something like 70 complex nilpotent conjugacy classes, and something like 10 of them are distinguished. All the others have tori in their centralizers and are therefore easy.
Any other questions? Thank you.
Okay. My original intent this morning was just to stand up here and read this to you in a very deep and booming voice, but I had this cough and I felt I couldn't do it justice. Anyway, if you want to see where I get nasty towards your friends, you have to scroll down. The web link is up there.
Yes, so I have, of course, a number of things to say on behalf of the director of the Institute and my colleagues at the Institute. This was our first big event after the pandemic. So we are extremely grateful to all the speakers for having made it here in spite of the well-known bureaucratic complexities of doing this. Thanks to all the speakers. We are very grateful to you. So that's my first thanks. To the young participants who have come from all over the country to attend this conference. I'm really thankful to you. Of course, the moving force for this conference, so Aprameyo from among my colleagues, but our senior mathematicians, Professor Raghunathan, Professor Deependra Prasad, who really made this conference possible. Hearty thanks to all of you. Right. So now I just want to make a couple of announcements. Of course, I recall that we have this excursion planned at 2:30. That's one thing. You assemble next to this building. Secondly, there is a lecture plan, an after dinner talk, let us say. So this is about 8:30, 9 o'clock in this very hall. This will be on the history of this institution. There will be a video talk, meaning there's a recorded video from the director who actually built this campus, Professor Mani, followed by a talk by Professor Raghunathan. So I welcome you all to that talk, which is at 9 o'clock after dinner. Thank you all. Thank you very much.